Describing color system based now on color perception. These were developed from a defining set of visual perceptions. So these systems aren't now based on primaries and a certain set of colorants, but it's something where it kind of begins in our mind. And it doesn't even require an actual set of samples. You know, all those other systems really were based on the samples that we had, samples that we can make. This is more of a conceptual system that doesn't even require samples. That doesn't mean you can't make samples. It's just you don't have to have them. And that's just one part of it. One thing scientists that work on these systems seem to always like to have is a concept called equal visual spacing. This enables us to interpolate visually between samples and facilitates classifying colors in fine increments. Everybody know what interpolation means? Two numbers or two things, and you want to get something in between. For instance, in the paint charts, if you went to the paint store and they have a page with a certain color on it, and it goes from usually lighter to darker, maybe a little greener, a little bluer, whatever, however it changed, and there's certain increments that it goes in. But you can perceive a color that's in between those two increments. I don't want to sound sexist or anything, but women tend to say, oh, I like this color and I like this one, but can you make something right halfway in between? That's interpolating. And if the formulas are all written for those cards, you can actually interpolate in between them. Sometimes with colors, that interpolation, you have, say, this color, and this is the one you want, and say visually it's halfway in between the two extremes, the two colors, you would think that you would divide the difference between the formulas and get exactly that color you want. That would be a perfectly linear situation, but it's not always the case. To get halfway in the middle, you might actually have to mix it closer to, say, this one, the right one, than the left one, to get it right where you want it. They like to set up in these systems is that there's basically a linear relationship you can interpolate accurately between extremes or two samples. With colors, unfortunately, most of the relationships are not linear. They are nonlinear, and there's attempts to make them linear, but they're not perfect. So a color order system is a conceptual system of organized color perceptions. And there's several of those. Color order system exemplification is a physical system that depicts a color order system. Color order system exemplification is some kind of actual physical depiction of the color order system. So you can actually look at it, move it around, feel it, that sort of thing. Going past just visualizing it in our minds. We talked about some issues earlier about practical applications of using the systems before. There are also some issues that if they're not sufficiently controlled when using the exemplification system for color communication, you have a problem. Again, this all gets back to communicating between, in the business, a supplier and a customer. Two people may not always be looking at the same color. So that's very, very important that the sample one person is looking at in the sample the other person is looking at is the same color. So some things you have to be aware of is that the viewing and illuminating environment can make the color look different. Different sources make colors look different. If you're looking at a color under daylight, customer's looking at it under artificial light, it's not the same color. It even could be the same sample, but it's not the same color that we receive. Viewing geometry can affect it. If you're looking at it straight down, or if you're looking at it on an angle. And some materials, and some plastics are like this, is that if it's, say it's this book here, if you look at it this way, you have one color. If you look at it this way, it's not the same color anymore. the exact same piece, but you perceive it as a different color. And I had an example of that at home a while back. In our living room, and we have a big great room walkway above it with the railing so you can look down into it, so you're way up and you look down, and we have a couch down there that has a fold-out bed in it. So you take the cushions off and you fold out the bed, and you can sleep in it, and then you put it back. Well, the cushions have kind of like the carpet here, you can see lines in one direction. My kids put it back together, which was amazing in itself. And I didn't have to. They put the cushions in there, and I was upstairs, and I just happened to look down, and I said, geez, those cushions don't match at all. I never noticed that before. So I went down there to see what was wrong. Well, they put them in backwards, and you could visually see a difference between them. So the geometry of how you look at something can sometimes affect what the color is that we perceive. We look at along the edge of the wall here, and there's a company in Fostoria called Ropey Rubber. They make the tiles. If you walk up the stairs here, there's the tiles with the round circles in them. They're actually rubber. But they make the tiles, the floor tiles, and then these borders that go around here. And it's amazing that the borders, if you look at them, and the tiles, if you look at them, when you put them in place, they match. They're the same color. But if you take it like this and put them both flat, they don't match at all. They're different. But when you put them up together like that, the perception that we see with those together, both together on those angles, make it look the same. So you have to be careful how you look at it. Put them in the right direction, right? Because they are directional. Not everything is directional, but some things are directional. When we get into plastics processing, we talk about orientation and machine direction and transverse direction. Sometimes that can affect the color that we see. It's not so much the color, it's the appearance. Color and appearance is intertwined when we're looking to match something. The customer doesn't care, well, I got the color right, but the appearance isn't right. That's good enough. You say, no, it doesn't look right. I don't like it. With geometry and the surrounding colors. That's kind of the example of the tile on the floor. Because that border is right up against a certain color, it would look different than if it was just, say, on the wall. The surrounding colors. Is the sample color constant? If you get a sample today and you look at it, if you look at it again in 6 months or a year, is it the same color or did it change? Things fade. They change color, especially if you leave them out in the light. So you want something that'll keep its color over time. You would like it to be in materials not sensitive to the environment. Nothing, again, degrades it because of something in the environment. Acid in the environment. Or sometimes I know, especially in automotive standards, we've gone to tours of Poly One or A. Schulman. They have plaques that are about this big that are automotive colors. Whenever they handle them, they wear white cotton gloves to make sure they don't get the oil from their fingers on the sample because the oil and fingers can make it look different. Matter of fact, there's an old trick that is used to make things look the same is that if you need a shinier surface on your chip, say then you have a shinier surface on your standard, you wipe it on your forehead, the oil from your forehead makes it shiny. You've got to be careful of how sensitive it is. And they can be made with high precision and accuracy. So when you make these one-cell chips, for instance, is every time you make a certain color, it always comes out the same. Like there's no variation in the color. And that can be difficult, especially in large production environments. The following conditions must be the same for the colors to be perceived the same. And the light source has to be the same, the viewing geometry has to be the same, and the surrounding colors. If one of those is different, the color is different. Sample quality, the samples must be of a constant color over time. Mentioned, don't change over time. Materials must not change with exposure to normal lab environments. Leave it out even just under the fluorescent light. Sometimes that can affect it. Ideally, you want to put samples away in a file cabinet or somewhere where light doesn't reach it. Sometimes extremes in heat, cold to hot, hot to cold, can change the color. Individual samples can be made with high precision and accuracy so that the same colors in different copies look the same. You can buy, each got one of these books, these Munsell student color sets, and in there are a bunch of color samples. The idea is they have to be made accurately enough so that every person has exactly the same colors that are labeled the same. So if you took your set of samples out and somebody else did and put them together, they should be the same. And if somebody bought it in China, that should be the same. Color order systems. Several examples of color order systems are presented here. I'll show you some of them. Munsell system is the most commonly used in the plastic industry. They've been around for, I think, since about the turn of the century. Last 20th century. All of them are based on ink systems. Therefore, any match made to one of the colors in its exemplification in a plastic system will be metameric. Now, there is a Munsell system in plastics, so you could buy a plastic system, but it's very, very expensive. Several $1,000s for that. So it's not widely used. So let's talk about the Munsell system. Again, the best known system. There's others, but this is a kind of a standard that's used in industry. Made for the ink industry, but it is also used in the plastic industry. It's not the best thing to use, but if your customer says that's what I want, you can't go and tell them, no, that's not the good thing to use. You have to say, okay, I'll do the best I can. So based on the principle of equal visual perception, I mentioned that before. So when we look at the colors in the exemplification, if we have a gap between two colors, then the next colors has the same gap between them and so forth, so that it's an even spacing between all of those samples. And there is a collection of samples available. This model here just shows a small number of them, but you can buy a larger book of all the Munsell colors. That these are just a few pages out of it. Distance between samples based on equal visual perception between them. And it was developed in 1905 as an art teaching aid. So this was made for art teachers, really. So it's been around a long time. It does have a numerical system to it. When we start talking about colors, we really want to use something that has numbers to it so that we can get very precise. If we just use names, it's very difficult to be precise about color. So the Munsell system does have numbers to it. So the physical exemplification is called the Atlas of Munsell Colors. And your Munsell Student Color Set book doesn't have all of them in it, but it does have some of that stuff. What we're going to do next week is actually use this book in class. So make sure you bring this particular book with you in class. Okay? But we're going to use that next week. Get your book or a book, but we're going to actually start looking at colors in terms of those three attributes that we mentioned, lightness, chroma, and color. Lightness, chroma, and hue. And put them in order. It's actually kind of interesting, kind of fun kind of thing. We'll do that next time. Munsell color system is a three-dimensional color space, and they call the different axes the Munsell hue, the Munsell chroma, and the Munsell value. In the Munsell system, they use, instead of using the term lightness, they use the term value, but it means the same thing. So there's 10 principal hues divided into 10 subhues. So what that means is 100 different hues that are in the system. So if we were to have every hue in the system in this model, there would be 100 of these pages all the way around. You can't do that. So the Atlas has all of those pictures, all those colors in there. Colors of objects, like I mentioned, typically described by those color coordinates. What we'll talk about, the first one is hue. If we look at our model, each page represents a different hue. And you could say blue, or then you could say reddish blue, greenish blue, You couldn't say yellowish blue. Okay. It's not just a single name for a hue, but the modifiers on there. So hue is that attribute of color which makes it appear red, yellow, green, blue, or a combination of those colors. I think everybody understands what hue is. Chroma is the attribute of color which describes its purity, or how much of it is that color in relation to gray. So a low chroma color is one that is close to gray. A high chroma color is one that is far away from gray. So if we look at our Munsell model again, if we start in the center, that's the lowest chroma material for colors. And as we move out from the center, it becomes more and more chromatic. The closer to gray the color is, the less chromatic it is. When we use these Munsell system and other systems that we're going to be talking about, we can use numbers to describe the chroma, the hue, and the lightness. So numbers can be used as well as names and relative measurements. As a color's distance from gray increases, the color becomes more chromatic and vivid. One thing to notice on these samples here is if you're real light or real dark, you can't get real chromatic. Higher chroma colors are, if you look on the pages, are generally in the middle of the page because you can't get a very light high chroma color or a very dark chroma color. Lightness is the attribute of color which defines its relative position on a continuous scale running from black to white. On our model, black is on the bottom, white's on the top, and it goes in varying degrees of gray as we go up and down. So pastel green is closer in appearance to white, so it's lighter, while a deep green is closer to black. We call that a darker. These are all terms that I think most of you are familiar with, but when we are in color, in the color business, all these terms have very specific technical definitions. So it's important that we understand what the real technical definition is, because these words are also used in everyday language, and sometimes the meaning is a little bit broader in everyday language than what we use as a kind of a technical term that we use in industry. So our Munsell color tree shows the three-dimensional relationship between the hue, chroma, and value. There's a picture of our Munsell tree. We actually have the real thing here. It's kind of interesting to see it all in relation to each other. So that would show the term that we used before, the color gamut of what you can make with the Munsell system. The Munsell Book of Colors is arranged on pages of constant hue. If you look in your Bill Meyer book, page 38 shows what it looks like. And also the pages in your Munsell student book also is arranged in terms of hue. So if we look at, for instance, this page here, that's a hue that's labeled 5 yellow red. And if you look in your little pictures here, there's a one that says 5 yellow red. But everything on a page, all those colors on a page, are all the same hue. That attribute for this system is held constant. The different chips in there, the different colors, then differ by value and chroma, but they all have the same hue. So the value from top to bottom goes from light to dark. The colors on the top of the page are lighter, the colors on the bottom of the page are darker. And the chroma, higher chroma are out to the right. The left side of the page is the least chroma. The right side of the page is the highest chroma. And there's a certain notation that goes along with the Munsell book. We have a number there, 5R610, represents a very specific sample of color. And you can actually interpolate between those. You could have like 10.3 or 10.5. You could do that too. What the 5R represents is that's the hue of the color. That's the page it's on, if you will. The value is what number it is going up and down on the page. And the chroma is what chip it is going out to the right of the page, away from the center. And by looking at those numbers, you could go in the atlas of Munsell colors and find that exact color. Your customer could say, yes, I want my color in polypropylene and I want it to be 5R 6/10 in the Munsell Book of Colors. And you would say, okay, that's what I need to make. Of course, the problem is that's printed and you're in plastics, so all those issues still are pertinent. But a customer could do that. The following slide shows an example from the Munsell Book of Colors. Your book student set gives you a chance to work with Munsell colors and pages. You can arrange these color chips correctly on the page. So that's what we'll do in class. We'll take the colors out, dump them out on one of the pages. It'd be a good idea to dump it out on the right page. And arrange them in order. And that's kind of challenging. It's kind of interesting. It's kind of fun. And when we do it, we'll probably do it at least in pairs because it's interesting to have a couple people work on the same samples because you may not always agree on the right arrangement. So it's interesting is you can look at them and very quickly kind of look at the whole page and see if everything's in the right place. Because if it's not, it'll kind of jump out at you. So we'll see that. Now, if they all look the same to you, then maybe next term you might not want to take another color class. They should look different to you. And here's an example of a picture of a page from the Munsell Book of Color. And you notice it says up there, matte collection. There's also a glossy collection. So one has a matte finish, which means a rough finish. One has a shiny surface to it, shiny finish. That's the basics on the Munsell system. We'll talk about it a little bit more detail when we start working with it next time. But those are the basics there. There's also another system called the natural color system, and it tries to use the eye's physiology and has 6 elementary colors, primaries if you will, black, white, yellow, red, blue, and green. And they're arranged in a 3-dimensional space also. Here they use a hexagon to represent similar but just a slightly different system. You know, all of these systems we'll talk about, take the same colors basically, and try to make some kind of sense on how you can organize the different colors and how you can arrange them. Similar to the Munsell book, you have a page of constant hue, and you have lightness and darkness. Again, you got to have 3 attributes, and they pretty much all use the same 3 attributes. Here's the color circle that's associated with the natural color system, and it's got some numbers up there that go with each one. This is also in your book. You'll see a little bit more accurate representations of what the colors are. But those are the different hues that are in that system. Supposedly natural colors, whatever that means. Here's a page from the atlas itself, like the Munsell page. It tries to use some lines and triangles there to represent equal visual perception. It shows up there, top right corner, what hue it is in terms of the circle itself. There's also a system called the color curve system, kind of a hybrid system. Uses C-Lab dimensions, and we haven't talked about C-Lab. That's coming in the next section. That's where we get all our numbers. We did our little calculation there. That's the basis for the C-Lab calculations and the C-Lab system. Easily exemplified in a variety of materials without metamerism, claimed by the manufacturer. This is a private system where there's a color cure or color curve system. There's a company called Color Curve that puts out these things. And if you look on the internet, there's companies that put out a lot of these. What I'll do too, I mentioned in the intro of the plastic class, is on your student portal, even though you're not using it necessarily for a distance class, these classes also are there. So if you look to your student portal and you click on, I think, academic, then courses, they'll give you a list of courses. You can click on this course and it'll give you a list of possibilities. There's one of them that says external links. And if you go there, I'll try to have some color links that you can go to and look at some interesting things. They're not necessarily requirements for the course, but just areas for more information. The intro color class or intro plastic class has areas in there for, say, chemistry and some of the things we're talking about there. Plastic trade associations, I have the SPE in there. Some of these company sites will be in there. So if you want to learn more about what's out there, you can go to those external links. Just a suggestion. Page from a color curve atlas or book looks like this. Different kind of arrangement, similar kind.